Let's dive into 1D dynamic programming, a powerful technique to solve optimization problems efficiently. In this video, we will explore how to solve problems using the concept of storing results in memory, instead of recomputing every time to improve the performance. We will look at classic examples like the Fibonacci sequence, climbing stairs, and the house robber problem. So, what exactly is dynamic programming? Dynamic programming is an algorithmic technique for solving complex problems by breaking them down into simpler overlapping subproblems. The key points are optimal substructure, overlapping subproblems, and memoization. Optimal substructure means an optimal solution contains optimal solutions to subproblems. Overlapping subproblems means the same subproblems are solved multiple times. Memoization means we store the solutions to subproblems to avoid recomputation, which is what makes dynamic programming so efficient. Let's explore dynamic programming with the Fibonacci sequence, a classic problem. The Fibonacci sequence is defined as f of n equals f of n minus 1 plus f of n minus 2, with the base cases f of 0 equals 0 and f of 1 equals 1. This means that each number in the sequence is the sum of the two preceding numbers. Looking at the code, we have a function called Fibonacci that takes an integer, n, as input. First, we handle the base cases. If n is less than or equal to 1, we simply return n. Otherwise, we initialize a DP array of size, n plus 1 with all elements as 0. We set the second element of the DP array to 1, since f of 1 equals 1. Then we fill in the DP array in a bottom-up fashion. For each I from 2 to n inclusive, we set dp of I equal to dp of I minus 1 plus dp of I minus 2. Finally, we return dp of n, which is the nth Fibonacci number. Let's compare the time complexity between the recursive approach and the dynamic programming approach for the Fibonacci sequence. The recursive approach has exponential time complexity. Each call to Fibonacci of n makes 2 recursive calls, leading to severe performance issues for larger values of n. The time complexity for the recursive approach is big O of 2 to the power of n. On the other hand, the dynamic programming approach has linear time complexity. The dynamic programming solution computes each Fibonacci number exactly once and stores the results in a table to avoid redundant calculations. Therefore, the time complexity for the dynamic programming approach is big O of n. Looking at the table below, we can see the drastic difference in time between the recursive and dynamic programming solutions. For an input of 10, the recursive time takes approximately 10 milliseconds, while the DP time takes less than 1 millisecond, which is a 10-fold improvement. As the input increases, the recursive time suffers drastically, while the DP time still remains very efficient. Let's look at another classic dynamic programming problem called climbing stairs. You are climbing a staircase. It takes n steps to reach the top. Each time you can either climb 1 or 2 steps. In how many distinct ways can you climb to the top? Looking at the code, we have a function called climb stairs that takes an integer, n, as input. First, we handle the base cases. If n is less than or equal to 2, we simply return n, since there are n ways to climb n steps. Otherwise, we initialize a DP array of size, n plus 1 with all elements as 0. We set the second element of the DP array to 1, since there is one way to climb 1 step. We set the third element of the DP array to 2, since there are 2 ways to climb 2 steps. Then we fill in the DP array in a bottom-up fashion. For each I from 3 to n inclusive, we set dp of I equal to dp of I minus 1 plus dp of I minus 2. Finally, we return dp of n, which is the number of ways to climb n steps. Let's look at another dynamic programming problem called house robber. You are a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. However, you cannot rob adjacent houses. Given an array of non-negative integers representing the amount of money in each house, determine the maximum amount of money you can rob tonight without alerting the police. Looking at the code, we have a function called rob that takes an array of non-negative integers called nums as input. First, we handle the edge cases. If nums is empty, we return 0 since we can't rob anything. If the length of nums is 1, we return nums of 0 since we can only rob one house. Otherwise, we initialize a DP array of the same length as nums, and set the first element of the DP array to nums of 0 since we can rob the first house. The second element in the DP array is set to the maximum of nums of 0 and nums of 1. Then we fill in the DP array in a bottom-up fashion. For each I from 2 to the length of nums inclusive, we set DP of I equal to the maximum of DP of I minus 1, meaning we don't rob the ith house, or DP of I minus 2 plus nums of I, meaning we rob the ith house and skip the I minus 1 house. Finally, we return DP of the last element, which is the maximum amount we can rob. Let's look at a general solution pattern for dynamic programming problems. First, define the state. This means we define what each element in the DP array represents. Second, identify the base cases. This means we set the initial values for the simplest subproblems. Third, find the recurrence relation. This means we determine how to calculate DP of I using previous results. Fourth, choose the iteration order, either bottom-up tabulation or top-down memoization. Finally, return the final answer, which is extracting the solution from the complete DP array. Let's look at a general template for bottom-up dynamic programming. First, we define the state. This means we need to determine what DP of I represents. Second, we initialize the DP array with base cases. Third, we apply the recurrence relation in a bottom-up fashion. For each I from 2 to n inclusive, we use a recurrence relation to calculate DP of I using previous results. Finally, we return DP of n, which is the final answer. Many 1D dynamic programming problems only need the last few states for calculation. In these cases, we can optimize the space complexity from big O of n to big O of 1. For example, in the Fibonacci sequence, we only need the previous two values to calculate the current value. As seen in the code, we can reduce the memory usage by only storing the previous two values. Comparing the time and space complexities, both solutions have a time complexity of big O of n, since both solutions iterate through n elements. However, the original dynamic programming solution has a space complexity of big O of n, while the space-optimized solution has a space complexity of big O of 1. These type of space optimizations can be applied to Fibonacci, climbing stairs, house robber, and other dynamic programming problems with limited lookback. So, when should you use dynamic programming? Dynamic programming is suitable for problems that exhibit certain key characteristics. First, optimal substructure, meaning the optimal solution contains optimal solutions to subproblems. Second, overlapping subproblems, meaning the same subproblems are solved multiple times. Third, decision-making, meaning each step involves making choices that affect future states. Fourth, counting problems, meaning you need to find the number of ways to achieve something. Fifth, optimization problems, meaning you need to find the maximum or minimum value. Sixth, problems with recursive solutions that have exponential complexity. In other words, problems where dynamic programming can significantly improve the performance. Classic examples of dynamic programming problems are maximum subarray sum, coin change, and longest increasing subsequence. In summary, dynamic programming optimizes recursive solutions by storing and reusing previously calculated results. 1D. Dynamic programming problems use a single array to track states with each element representing a subproblem. The recurrence relation is the key to formulating a dynamic programming solution. The bottom-up tabulation approach is often more efficient than the top-down memoization approach. Space optimization can reduce big O of n space complexity to big O of 1 in many 1D dynamic programming problems. To solidify your dynamic programming skills, make sure you practice problems such as Fibonacci number, climbing stairs, house robber, maximum subarray, coin change, and longest increasing subsequence. Thank you. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.